Norton's theorem. Any two-terminal linear network with current sources, voltage sources and resistances can be replaced by an equivalent current source with parallel resistance. The value of the current source is the short circuit current between the two terminals of the network, and the resistance is the equivalent resistance measured between the terminals of the network with all energy sources replaced with their internal impedances. This is our network having voltage source and current source and the resistances with a load R4. Now this can be replaced with a current source and the resistance in parallel between the terminals A and B. This is the current IN. Short circuiting current is also known as Norton's current, and this is the resistance known as Norton's resistance. This is the current obtained by short circuiting the terminals A and B and replacing the energy sources with their internal impedances. Here we have voltage source, this should be short circuited, and here we have current source, this should be open circuited. By looking from here, this R1, R2, R3, then R Norton's is equals to R1 plus R2 in parallel with R3. This is a Norton's resistance, whereas voltage source and the current source Vs and I with R1, R2, R3, and this is terminals A and B. This is the current flowing through this is Norton's current IN. Verifying Norton's theorem with a given network. Find the current through 6 ohm resistor. This is given network. Usually we will calculate the current through the 6 ohms resistor, that is I6, equals to total current flowing through the network multiplied by opposite branch resistance divided by the sum of both the resistances. Whereas the total current flowing through the network is given by the total voltage divided by the total resistance of the network. In this network, if you observe, then 5 ohms plus these two are in parallel, so 10 and 6 ohms are in parallel. So if you calculate this value, this will be near about 2.285 amps. Then I through the resistor 6 is equals to 2.285 multiplied by 10 by 16, which equals to 1.43 amps. This is the general way of calculating the current through the resistor 6 ohms. Now let us try to find out the Norton's equivalent circuit. Then this can be replaced with a current and in parallel with the resistance of the Norton Rn between the terminals which are connected to 6 ohms. Now we need to find out this IN and Rn. Finding IN, this is 5 ohms, this is 10 ohms, 20 volts. These terminals need to be shorted. Current I flowing through this is 20 by 5, which is nothing but 4 amps. Since in this parallel paths, this is having the resistance 10 ohms, whereas this is not having any resistance, so the current takes this path. So IN is 4 amps. Finding Rn. While finding the Rn value, we need to replace energy sources with their internal impedances. So I am replacing this 20 volts with a short circuit, and this is 5 ohms and this is 10 ohms between the terminals, that is A and B. So A and B. Then this is the resistance seen from this side. Then we can say that the 5 ohms is in parallel with the 10 ohms. This is Rn. Then if you find out this, then 50 divided by 15, which is nothing but 3.33 ohms. So this is 3.33 ohms. Now connect the resistance R and let us find out the current flowing through resistance 6 ohms, that is I6, is equals to the total current, that is 4, multiplied by the opposite branch resistance, that is 3.33, divided by the total resistance, that is 3.33 plus 6, that equals to 1.43 amps. Hence it is proved that the 6 ohms has the same value of current both in original circuit as well as Norton's equivalent circuit. So for this circuit, this is our Norton's equivalent circuit with the Norton's current 4 amps and Norton's resistance 3.33 ohms.